Okay, so we move to the last speaker, Karim, who is a home player. He's playing at home. He's a postdoctoral researcher at in the lab, COSIC, of course. So he's going to talk about not CSI-FiSh, but CSI-SharK. So Karim. Yeah,
Thank you very much for the introduction. Hello, everybody. As you can see, yeah, the title of our paper is CSI-SharK. Basically stands for CSI-FiSh with sharing friendly keys. And as you can see, so basically it's related to three-shot signatures. And this is joint work with Shahla Atapur and Daniela Kozo and Robbie, that two of them basically are sitting here. And you can see the basically paper in this address. So yeah, thanks to the previous presentations, we already had enough, I guess, introduction. Just I want to say that we are in the hard homogeneous spaces, and with this notation that we use basically G power A, acted on this curve E is shown by this bracket notation A on E. And so for just saying that what is the ID protocol, because we will use ID protocol to build a signature. So ID protocol allows you to prove that your identity, basically. You prove one secret key for a public key. You expect that this protocol guarantees some security properties that are known as correctness, spatial soundness, and honest verifiers range, that we had a very nice, explanation about them here. So just I want to emphasize that it is already proven that in the quantum or also standard random oracle model, so using fiat chamber transformation, you can transfer any ID protocol to the secure signature scheme that you want to build, basically. So I want to start with the ID protocol behind the CSI-FiSh, because we want to modify this protocol to achieve to the CSI-SharK. So in the CSI-FiSh, the basic ID protocol is constructed for gap or vectorization problem, that you want to prove that you know this A in between these two curves. So to do that, basically, as we already observed, so one approach is that you basically commit to some different curve called EB, and then you are challenged to open basically one of these links, either that you know this committed value, or you know the link between committed value minus the secret. So you see that in one case, you have to know this A to open it. And based on that, basically the soundness rate, error rate of this protocol is 1/2. So you can cheat with probability 1/2. So to decrease this probability, you can amplify this protocol by repeating. So you can repeat it lambda times, you will achieve to the soundness rate 1/2 over lambda. But in practice, repeating this many times will give you very large signatures. So one idea is that try to increase this 2 somehow. So this is basically the extension of the challenge space. So there is another cool idea that basically says you can, instead of building, proving the relation between two curves, so you can try to prove the relation between many of them. So basically you extend the public key and you say that I know the link between any two that the verifier picks. The ones that you challenge, basically. So this is called multi-target gap problem, which basically is assumed to be, again, hard. So again, this is the same that's happening here. So you have this, again, the commitment, the red ones, then you get challenged, but now instead of binary challenge, you have 0 to k-1. And then again, you open the same response, but now the one that you are challenged, basically. So now you can show that the soundness rate is 1/k, because from these plots, you can see that you can open this just the blue one, but not the others without knowing the secret. So the challenge rate, the rate that you can cheat is just 1/k. So by repeating this k, now instead of lambda time, you just repeat t time, smaller than lambda. Basically, you could say lambda divided by log2 of this k. So you can achieve the same, protocol, ID protocol, but a different language. Still, this is sufficient for building a signature. But the good point is that now this T is smaller, so we need to repeat less. So we can build more efficient signatures, let's say shorter signatures. So in the twist case that if you work with basically symmetric HHS, so you can have even slightly larger challenge space that you can compute this division around the E0. So based on that ID protocol, CSI-FiSh basically just is obtained by, applying fiat chamber transform basically in the quantum model to this ID protocol and obtain a signature scheme, which is exactly the same description of the ID protocol. So you sample, EK curves using different secret values of A1 till AK-1. And then you set this SK and the others as a public key. And in the signing, you follow this ID protocol, but you make it non-interactive using random oracle, which basically are instantiated using hash functions. And the verification is just following, the protocol and just computing these challenge values from the sent messages and checking that if these sent challenges are the same, that should be based on random oracle. But if you want to build a tree-shot signature based on this, so you basically have to deal with this group action in the distributed manner. So of course, maybe I should mention that tree-shot signatures are just signatures that the key generation and the signing are distributed between several parties instead of one party. So the simple example is that imagine that we have Alice and Bob. They want to compute this E1 is equal to A acted on E0, and A is just A1 plus A2. So in a discrete case, it was easy. You could just compute G power A, G power B, and then multiply them together and obtain this. But here, unfortunately, we don't have such operation. So, and the solution that is proposed by the first, tree-shot signatures is just following the round-robin protocols. First party computes this G power A, let's say, and gives it to the second party, then the second party computes G power A times B, that here you see for isogeny setting. Based on this idea, basically round-robin communication, we have several tree-shot signatures. The first one was basically the one by Defeo and Mayer, that it was passive secure, and it works with Shamir secret sharing. And since it is passive secure, so it is more efficient, so of course. And at the same year, we had a nice protocol with called Sashimi by Kozo and Smart. And they achieve active security basically by adding zero-knowledge proofs to such protocols. But they work with replicated secret sharing, and they don't need basically trusted third party to do the key generation. They have a distributed key generation protocol. And the initial two ones are signature scheme. They have signing and basically key generation protocol. The third one is called basically Sirashi, which is a distributed key generation protocol, which allows you to basically generate this E1 is equal to A acted on E0 in a distributed manner with same people from COSIC, almost they are here. So this protocol is robust and active secure, but both these last ones that are active secure and using zero-knowledge proofs, severely, they are a bit slow. So I would say very slow. We will see in some instantations. For example, you will see that, based on some estimation in Sashimi, two parties can sign a message in 283 seconds, almost 5 minutes. And also Sirashi says that for generating just one key, you need 4.5 plus 18n. N is the number of parties. So basically 40 seconds for just one key. So if you have 1,000 of these keys that we have in practice, you have to spend 40 times 1,000 seconds. So, these three protocols, are tree-shot signatures and distributed key generation based on CSI-FiSh. I wouldn't go through the description of these algorithms, rather just go into the efficiency of these protocols in the key generation and the signing by just operations that they need to do, because we want to say that we can achieve efficiency on doing this by C# based protocols. So here I just have the key generation, key generation and the signing of, let's say, passive one, and this is the Sashimi active one. And here we have the Sirashi, basically this is just key generation, not signing. So in all of them, almost, since we have K-1 keys in the CSI-FiSh, so you have to do many things K-1 times. You have to do K-1 times, secret sharing K-1 times, committing K-1 times, proving, and then you have to use this commitment to generate a key. Again, you have to repeat this K-1 times, many things K-1 times because of this K-1 times secret key. So in practice, let's look at what are these numbers, usually K. So if you look at the paper of CSI-FiSh, these instantations are even in middle, that you have K equal to 2 to 12, we can have even 2 to 18, and T is equal to 9. Sorry, K is 2 to 12 and T is equal to 9. So you see that keygen can be 450 times slower than signing. It's huge gap. So this was our motivation in this work, that can we basically get closer numbers. So we presented C#, basically is the CSI-FiSh just simply changing its public key to the something with just one secret key instead of K of them. And we show that it's as efficient as the previous one. It has just single secret key. And the only issue is that we rely on a new assumption that we recently ourselves, introduced recently in a different paper. And we show that, unfortunately, the only and the currently actively secure threshold signature, which we mentioned, sashimi, is not secure. Actually, in the threshold setting, there is an attack against the key generation that a malicious adversary easily can cheat. And in the signing protocol, even honest parties cannot assign the message. And then we, based on C-SharK, we present a variant of this new, the mentioned protocols, and we show that they are quite efficient in the key generation. And then we propose some maybe not interesting from the theoretical point of view, but very interesting from practical point of view, that some strategies that you can use in almost all of these protocols, that now we say some optimizations that are very important, I guess, because yesterday or a few days ago, I was in a talk that they said isogenic threshold signatures are not practical, but now we will see that these optimizations, to be honest, they are close to practical. So yeah, we started with the ID protocol behind the CSI-FiSh. We started to modify it. So what was our modification? Recently, in a different paper, we introduced structured public keys. And what is a structured public keys is basically this public key of the CSI-FiSh. But instead of generating with one different secret keys, we just sampled one secret key. And we used some exceptional, set. We will say why they are important. So we generated this public key with different factors of the same isogeny A. And this coefficient C0, C1 till CK are public. And we claim that still this is difficult. And we show that if this is basically difficult, that by now it seems to be difficult. So we show that in that paper, basically we can extend this challenge space of the basic ID protocol. You saw that once we extended the challenge space of the previous ID protocol in CSI-FiSh, we had to change this language. We couldn't prove that really we know this A. We just proved that we know the differences between two. But with this technique, we could exactly prove that A. But the problem is that we need to trust a third party in that protocol. But there is one cool thing. So now we introduced a new assumption, which says that given this structured public key, still you cannot obtain A from this structured public key. So now this is our key idea. Okay, let's take CSI-FiSh, and just instead of generating case randomly, generate like this, but the verifier still doesn't need to trust anyone, because we will, again, similar to CSI-FiSh, we will prove that we know the differences between two. So we have the same statement as CSI-FiSh, but instead of generating this with random ones, we just take one A and generate a structured public key. So now, similar to the previous case, we have the same commitment and we have the same challenge space. So we just have also the same opening, but instead of having, let's say, D indexed by A, now we have D times A, because we have generated secret key in that form. And in the opening, you will open one of these, dash blue lines. So again, we can show that this protocol is a special sound. Basically, we can extract a witness still, because for the verifier that you wanted to show that it's still a special sound, it doesn't matter that really you generate it independently or you generate it by something secret times something. So that is the reason that we can still extract a secret, but now maybe the secret has this structure, CA times A minus CJ times A. But it doesn't matter for verifier because it's already difficult. So it's enough for building a signature. In the case of CSI-FiSh, it was just ACI minus ACJ. So for verifier, nothing changes. Just the prover changes the sampling these keys. And again, the soundness rate is 1/k as CSI-FiSh, and you need to repeat the same number of times. This is one reason that why we have the same signature size and the signature protocol. But the keygen would be different in threshold case. So yeah, almost the same signature as CSI-FiSh, but instead of having different A's, we have just one, but using a exceptional set. Exceptional set is that 2 by 2, these elements, some of them are invertible to modular this n that you work in the system. So the verification is the same, just signing is instead of opening A indexed by DJ, so you have DJ times A. So now what if you want to make threshold protocols based on this? So we have nice, points here. So we have just single secret key, so we will have single secret sharing. So we will have single secret sharing, we will have just one, let's say, secret share to communicate with IDs, parties, I mean. And if we have single, basically secret sharing, we can have just single zero-knowledge proofs to prove that you know this commitment. Many places you can remove this K-1, we will see. And just the important point is that now that we have structured public keys, so you don't need to repeat one proof for this bottom statement K-times, but instead you need to give one proof but for a slightly larger statement and language. So you have to prove that the commitment, the B that I have committed is used in whole structured public key. And in this case, always they were just two elements, basically two curves. But here you have K plus 1. So basically this K is 1,000. Now you see that 1,000 times more, 500 times longer than this. So we saw that basically using this C-SharK, now we can remove many of these highlighted parts. Instead of K-1 in this passive one, you can just have 1, 1, 1. But the dominated part is this K-1 group action, because you see that we have the same public key, so you cannot bypass this. You have to compute this K elliptic curves. So this is the same also, the active one and the passive one, all of them, and also in the hierarchy. Everywhere that we had K-1 because of K-1 secret key, we can remove it. But since the public key is K-1 curves, still we have this K-1 group action. So yeah, this was the protocol that we had basically in the three-shot case we presented. I don't go through to the protocols. You can go to the paper, but I would like to show some important optimizations and their efficiency. So one thing is that you notice that based on the length of K, we need to repeat this T times in the signing. Also, even if you want to generate this K, so we have 1,000 of these curves. So one important thing that is that the previous work have missed is using multi-core CPUs. So we noticed that if you use multi-core CPUs, easily by the number of cores, you can divide this cost. And you will see that this is very important. For example, if you go to the table in the CSI-FiSh that is based on single core, so you see that if you want to achieve some numbers that are milliseconds, so you have to increase this K. But we show that you don't need to do that if you use multi-core CPUs. So just take the small 1K, basically public key, and the signing is this as before, but you will have, instead of 1.2 seconds to sign, you will have just milliseconds. This is because you saw that if you have this K2 to 10, you have to repeat, let's say 10 times. And 10 core is a standard over, our CPUs these days. And this is, interesting point to basically use isogeny stuff in practical protocols. Another point is basically these three-shot protocols. You saw that again, we have many of them, but now you have to do this stuff with a multi-party protocol. So we said that for one case, we have to follow the round-robin protocol. For example, if you want to generate this, so this public key, so your party one has to do this, pass it to party two, and party three, blah, blah, blah. But one may notice that basically you don't have to do this, because if this K is 1,000, so we don't have 1,000 CPUs in each party. So instead, what you can do, you can basically divide this curves among the parties, and party one can start with this, let's say, these curves, and party two can start, party B can start with this one. So you don't need to first party to do the 1,000 curves and give it to the second party, and then he will do that. No, you can give 100 to the first party and 100 to the second party. They can start because it doesn't matter. They just have to update it one time. And then you basically, reach the same public key that you wanted, but in a parallel round robins instead of just one single consecutive round robin. So, and in the CSI-SharK setting, we have this issue that I mentioned. We have a huge zero-knowledge proof. The statement is quite long, 1,000 curves. So sometimes we don't have also 1,000 CPUs. So what we can do, we show that you can divide these proofs. Instead of proving one huge proof, so you can divide this proof to the several parts, because what you need is that I just want to prove that I use the committed curve, this isogeny, to compute this structure public key. But of course, I can divide it to two proofs that I use the same commitment for first half, and also the same commitment for the second half. So you can divide, and we show that for some special values, this is optimal, in a particular setting. But this is just for C-SharK based protocols, I say structure public key based. Yeah, we observed that basically this gives us very nice improvement, these optimizations. So you may notice that, for example, yeah, here you can see C-SharK and CSI-FiSh in the single core case, 16 core with 3 parties and 8 parties. So the first table is full 3-shot because we show that sashimi is not secure in 3-shot case, but it is secure in full 3-shot. So we use the full 3-shot variant of it. So we show that basically you see that simply by just moving from single core to the multi-core, you see how much we can improve 4.5 hours for 18 minutes. So they are quite practical if you really have multi-core 16-core CPUs. And also in the Sirashi, you see that 4.7 hours to 18 minutes. And the other point is that communication between parties and also the secret key size in the C-SharK gets very small because we have just naturally one secret key. Communication is small, so you can, see them here as well. And also signing protocol in CSI-FiSh and CSI both are the same. But the point is that we have new optimizations, and the number that was reported in, for example, sashimi 5 minutes, it doesn't need to be 5 minutes now. It can be even with 3 parties, not 2 parties. It can be 18 seconds. 18 seconds, yes. 28, sorry, I cannot see it from there. Yes. So, and the other point is that we have similar improvements for structured version of the Sirashi. And you can basically have a very nice improvement on, let's say, the running time of that you would see here. One thing that I should mention is that, so you see that here, this is with a naive approach of CSI-FiSh version. So you see that by just moving from CSI-FiSh, to the structured public key, you also have very nice improvement from 80 minutes to 4 minutes. And then, yeah, this shows that 3-shot signatures based on isogenies also are more efficient than what people think, I guess. And for more discussions and results, you can just look at the paper. I didn't go through the details of the constructions and the attack, especially against the sashimi, but the attack is based on this replicated secret sharing. That in replicated secret sharing, you have more than one share. So you have to add, if you have a qualified set, one party has to add these shares together, and then you add them together, you cannot verify it. Basically you have to give a proof, but they haven't given it. Thank you very much.
So thank you, Karim. We have time for one full question now. Yeah.
So I want to ask about this new assumption. So you prove that your scheme is even actively secure if this assumption holds, right?
Yes, the ID protocol relies on that.
Yeah, and did you do any reductions from this assumption to like something more standard? Or it's a completely new assumption.
I would say that we try to reduce it. Oh, sorry, it's go. We tried to reduce it to multi-target gate, but we couldn't. The reason is that here we give extra information out. The point is that in multi-target gate, you sample them with random things. So you don't say that which one is generated with which one. But here we say that you generate one structured public key with one secret key. And even if I give you this public factor C till some special upper bound, so you still cannot learn. So we couldn't reduce. Actually, this is maybe one interesting question to this follow-up discussions, that if we can reduce it to something. Co-authors, we couldn't reduce it to multi-target cape or something similar.
And what's the condition on the CI? They are just
they are from exceptional set. Yeah, to be hard. So in the basically standard case, this SSH, we need to be from exceptional set that's such that this minimum, factor of this n we have is smaller than, the k is smaller than the minimum factor of this q. This zn that we define. This n is the smaller, factor of this prime factor of this n. But in the twist case, we need even smaller, divided by q over 2. The reason is that we have also -1s, so we need to have a smaller set. But in practice, this is more than 2 to 20. We don't need 2 to 20. We need 2 to 10, for example, is enough for practical protocols. Actually, we have this, I should say that I'm from zero-knowledge background. So ZK snarks, we have an alternative in discrete log for snarks. So we see that given G power X power 1 till G power X power Q, you cannot learn anything about X. And this is analogous to that in the discrete log, which is called discrete log with auxiliary information.
So let's thank the speaker again.
Thank you.